Hello everyone, today I'm excited to introduce you to the McGinty AI Fractal Spacetime Academy, an educational platform that explores the theoretical frontiers of quantum physics through the lens of fractal field theory. What you're seeing on screen is a cutting-edge visualization interface that helps explain the McGinty equation, or MEQ, which is a framework that describes how space itself might be folded through fractal resonant topology rather than traditional wormholes or Einstein-Rosen bridges. This mathematical framework provides fascinating insights into how quantum physics and fractal geometry might intersect in ways we've yet fully to explore. The platform is divided into 5 intuitive sections. The introduction, which explains the core concepts, the MEQ basics, which breaks down the mathematics, folding space shows the mechanics of spatial folding, a simulator, which is an interactive playground to experiment with the different parameters, and then applications, exploring theoretical uses and then future research. We'll walk through each section to understand the revolutionary concepts. The introduction provides an overview of what the McGinty equation represents, which is a paradigm shift in quantum field theory that incorporates fractal dimensions to explain non-local phenomena. Unlike traditional wormhole theories that require negative energy and exotic matter, the MEQ proposes that space folding occurs through fractal field resonance, where two dissonant points become topologically adjacent through field phase alignment. You can see a visualization down here representing the nested fractal dimensions in quantum field theory space, which is a key concept in understanding how this theoretical framework operates. So the MEQ Basics tab. Here we dive into the mathematics. The extended McGinty equation unifies quantum field theory with fractal dimensions and gravitational effects. The equation has four key components. The standard quantum field theory wave function, the fractal dimension field component, gravitational effects, and then the topological folding term that connects distant coordinates. As you can see, we have interactive sliders. Epsilon controls the fractal field resolution, phi governs phase angle alignment, and then our resonance frequency determines the coupling strength. When you adjust the sliders, you can see how they affect the mathematical properties of the fractal field. The innovation here is introducing non-integer dimensional analysis, which allows for new approaches to quantum phenomena. This is the folding space tab. This section explains how the folding mechanics actually work. The McGinty equation enables a new approach to spatial transport by modulating fractal field topologies to collapse spatial separation via resonance coupling. We have a visualization of the fold mechanics. The red point represents our origin point. The blue point is our destination. The normal distance between them is shown by the dotted line. When I click Calculate Fold Strength, the system computes the theoretical amplitude based upon our parameters. A curved path could appear, representing how the fold would connect these points through fractal resonance rather than traversing normal space. Below, we have expandable sections with detailed mathematical explanations of each component. The folded metric tensor, the transport probability field, the folding field Lagrangian, and the causal horizon synchronization, which ensures that we don't violate causality. Now for the fun part. our interactive simulator. Here you can experiment with all the parameters and see real-time visualizations of the folding effects. We have our control panel with the sliders for fractal resolution, phase angle, and the harmonic frequency. We also have our intent input field, where I can enter symbolic destination using the consciousness syntax language or cognospheric language. As I adjust the parameters, you can see how the visualization updates in real time. The glowing fields represent the fractal field density, while the curved path shows the potential fold connecting our origin and destination points. When I click Compute Fold Strength, the system calculates the fold amplitude based on the current parameters. If the value is high enough, generally above 0.7, we achieve a stable fold that theoretically allows for transport or information exchange. You see how that path changes and the fold strength changes depending on the parameters that you put in. Below here, we have the resonance spectrum, which shows our selected frequency that we're at, and then the phase coherence display, which shows the alignment between the origin and the destination points. Finally, let's explore the applications of the theoretical framework, which are the mathematics suggests several very intriguing possibilities. Quantum communications, potentially enabling instantaneous information transfer, spatial transport. While physical transport remains theoretical, the framework suggests possibilities for quantum state transfer and computing applications with the potential for revolutionary approaches to quantum computing. We also acknowledge some of the challenges, from some of the theoretical limitations like quantum decoherence at macroscopic scales to engineering challenges, like generating the required frequencies. But these are just engineering challenges. The math is very solid, so I've got a lot of confidence we're going to get to where we want to be. And that's where we have our future research directions as well down here. And that's just where we want to, theoretical exploration continues, from quantum fractal materials to computational models and experimental validation approaches. The McGinty AI Fractal Spacetime Academy represents a bold exploration into theoretical physics. It really pushes the boundaries of our understanding of quantum mechanics, fractal geometry, and spacetime itself. While it remains theoretical, rather than an engineered reality at this point, it is a very fascinating model to show how space might be understood and potentially manipulated through the principles entirely different from our conventional understanding. I hope you enjoyed this tour of the platform. Whether you're a physicist or a student or simply curious about cutting-edge theoretical concept, the McGinty AI platform is an intuitive and a visually engaging way to explore these complex ideas. Thanks for joining me in this demonstration.